let's look at how we can use these reactions, or how they may be used. Electrochemical cells have the reactant and product separated so that there's an electric current involved. In a voltaic cell, the reaction that is going on is a spontaneous reaction. And so the electric current that is involved is one that's produced by the reaction. Okay. The opposite of that is an electrolytic cell. An electrolytic cell, you have to put the current on it in order to drive or make a non-spontaneous reaction occur. In a way, you could think about it as when you're using a battery, you have this reaction going, it's acting as a voltaic cell, but when you're recharging a battery, you're applying an electric current to make the opposite reaction, which is non-spontaneous, to go. I say voltaic cell, that's the more common term, but galvanic cell is the same thing. A little bit about electrolytic cells, and we're not going to do too much with it, but I want you to know the definition. It's where, so I have a power source here that is driving the current and making the reaction occur rather than the other way around. This little E cell is the cell potential, and it will be a negative number for an electrolytic cell. We will get back to that with the voltaic cells. Amps or ampere, that's a measure of the current that's required. And in this case, we're having a salt, sodium chloride, being separated into its elements. That is not a favorable reaction, but when it's hooked up to a current, we can get that to occur. We're going to do a lot more with voltaic cells. These are the ones that take a spontaneous reaction and create the current. Okay, and this is a simple one that involves two half reactions with zinc and copper. And for each one, we have a container with the solid metal zinc and a solution that has zinc ions. On the other side, we have a solid piece of copper and a solution with copper ions. In between, we have what's called a salt bridge. We'll get more into that. We call this whole apparatus the electrode. And so the electrode includes both the liquid and the solid. The solid, if you want to know what that's called, it's the terminal. And on this one, if we look at the reaction, we see that zinc is giving up electrons, and so it is sending electrons over to copper. Copper is accepting those electrons and becoming copper that's neutral. Also, we talked about these as being half reactions up here. We could refer to this cell, we call this a cell, it's actually a half cell. A cell would be the whole thing. This is a half cell, and we might call this the zinc plus 2 half cell. Let's look at what's happening in this particular voltaic cell. If we looked at the reaction, zinc was losing electrons, and so that means that zinc that was neutral, part of the metal that's sitting in there, is sending electrons off this way, and it's becoming an ion. So this terminal is going to slowly shrink as the ion's going into solution. The electrons come over here, and when they get on the outside near the solution, that's where an ion floating up can accept those, and it will cause it to become the solid, the neutral solid. So this electrode actually plates out. The copper will plate out. It looks like it's dissolving in this picture that I got, but actually this one would be growing. It would be getting bigger. So the electrons that are lost by zinc are going up through a wire, and it's going through a light, and of course the movement of electrons, this flow of electrons, that's what electricity is. So that flow of electrons is a form of work, and it's making the light bulb light up. Also about the salt bridge. So a salt bridge, they work different ways, but the idea is that they allow the charges to not build up. Because if we did not have some way of keeping this neutral, this solution would become positively charged because it's constantly making these zinc ions. Okay. So the salt bridge has ions in it. It's a salt bridge. It has an ionic compound in it. And so negative ions can come out of this and help neutralize the positive charge. Positive ions can come out of this and help neutralize the negative charge that's caused by all of the ions leaving, the copper ions leaving. But anyway, we usually don't treat it as those reactions as too important because we're really focused on the redox reaction. So that's the purpose of it. Some more definitions. The anode is the electrode where oxidation occurs. And remember, when we say electrode, electrode is this whole thing. This is an electrode. Okay, so you need to remember that the anode is where oxidation occurs. And I remember this because of the vowels. Anode, oxidation. And cathode is where reduction occurs. So if we look at our half cell reactions, which one is the cathode? So where does reduction occur? It would be the copper. So this is the reduction. This is the oxidation. And so we could label that down here. Go ahead and put anode. The sign of the anode, in other words, we always assign the anode a negative sign and the cathode a positive sign. And our way of thinking, chemists' way of thinking about it, is that electrons are trying to get away from this negative sign. So electrons flow from the negative to the positive. In other words, from the anode to cathode. So have these relationships in terms in your head, just kind of like you had to remember heat of reaction was negative for exothermic, and the water warmed up for that. You need to kind of have these relationships in your head. So on this one, this is our these are our half reactions. So the net cell reaction is just this. And the last thing we want to note is that it is the convention to draw the anode on the left. It's always on the left, and the cathode is on the right. For our cell notation, we always show the anode on the left, and on the very end, we'll put the anode terminal. The bar represents a phase boundary. The double bar represents the salt bridge. And again, we have, this is the anode and this is the cathode. Okay, and on each side, when we look at this, this is the order of the reaction, that it's going, copper is going from +2 to neutral, and this is the half reaction. Zinc is going from neutral to +2. So those do represent the half reactions in that order. In other words, I would not want to put the zinc with the +2 here. Also, this kind of cell notation is called a line notation.